Okay, we're live. All right, so last time we were talking about um, Boolean expressions, right? And I mentioned we were going to look at some of these Boolean operator things, and we're going to look at if statements and kind of keep moving on our list of how human beings solve problems, remembering stuff, asking questions, repetition. And remember, 100% of programming languages will have facilities for emulating those three things. So as soon as we know how to do those three things in a programming language, we basically can do all sorts of stuff with that language. Okay. So at this point, you've already learned 1/3 of C++ when you put it in that context. All right. So we're going to learn if statements between now and call it next class. Then we'll get into loops and functions, and then we'll start solving more complex problems. All right. Somebody last class had asked, like, what are the, how complex does this class ultimately get? The last portion of this course, we start writing kind of an old style game called MUD, multi-user dungeon. So it's kind of a Dungeons and Dragons-y type thing where you have a player who's going through a dungeon, heading north, south, east, west, fighting against rats or whatever monsters we choose are in there. We're going to have hit points and damage rolls and all this stuff. So you'll basically be able to write a text-based video game when this class is done. We start off the next course um, continuing on with that, and then we port it over to a visual type game with the Unity game engine. And then we'll start adding other cool stuff. If we have time, we might even bring it into virtual reality. We'll have to see, but that sounds fancy on paper, but the difference between a VR game and a normal 3D video game is the camera. You're just changing out the camera from a single point of view camera to a camera that automatically moves when you turn your head. Right. And then you have to redefine the controls because instead of, moving with maybe the arrow keys or moving with a controller, you now have these hand controls with joysticks on it or whatever. So you just rewrite the if statements that determine what happens when you press up on the thumbstick on your right controller. Okay. It sounds more complicated. Well, in your mind, it's probably more complicated than it actually is. All right. So we'll see where that goes. But even if we don't get into VR stuff, you will have all the skills you'll need to jump into VR stuff then. All right. So I promised you that I would trick you a little bit today. I'm teaching you a couple of things that are things you might bump into by accident that technically are not errors, but give you freaky outputs. So I'm going to try to bring some sense into why you're getting that output, and then you can throw it on the back burner because it's not something that you really need to worry about, frankly, in this class, but it is something that's going to help you with a debugging type of approach. All right, so today we're focusing on these ideas of Boolean expressions. And we mentioned last time that a Boolean expression is any expression that boils down to a single value of true or false. All right, doesn't matter how complicated it looks. You can have all sorts of ands and ors and a whole bunch of things strung together, but at the end of the day, it comes down to a single true or false. Okay, so for instance, we could say, is it sunny outside and is it raining? That would never be a true statement, right? I guess technically you could have a sunny day with one of those sun showers or something. That could happen, I suppose. So it'd be an unlikely true statement, but a potential true statement. Okay. Typically, it would not be cold and hot at the same time, those kinds of things. All right. So let's look at these things. So let's start off with and call it the and truth table. All right. So an and is true only when both sides of the expression are true. So that is to say a true and true is equal to true. A true and false is equal to false. A false and true is equal to false. And a false and false is equal to false. All right, so the only way for an AND Boolean operator to boil down to a true value is if both sides of the expression, the left and the right side of what's on the AND operator, this double ampersand, if both sides of that is true. So that's our only case when we get a true value out of that. All right, we're going to be leveraging these Boolean expressions inside of if statements here pretty soon, but for right now, they only exist as just Boolean expressions, whatever we're going to use those for. Okay, so that's the what's called a truth table, the AND truth table. The OR truth table, actually kind of steal this. This guy is false only when both sides of the expression are false. So true or true is true, true or false is true, false or true is true, false or false is false. So the OR truth table says that only when both sides are false is the entire thing false. So if at least one side is true, the whole thing will be true. Now, an important thing to keep in mind with this. So are we gonna, give me another slide? All right, so let's call this a coding caveat. When the computer is processing a Boolean expression from left to right, as soon as it can make the determination that the entire expression will be true or false, it stops checking. And what that means is, so for instance, if we're looking at the OR truth table, and we look at the second one right here, as soon as we hit a true, do we even need to check the rest of this to know that the output will be true with an OR? We know we don't have to check it. The computer does too. And this is actually an important thing because sometimes you might have a situation when you're writing a Boolean expression when this second value here might actually be like something called a null pointer exception or something. It might not actually have a value. It would only have a value in it if this guy failed or something like that. So it is to your benefit to know that it won't even check that second guy if the first guy does its thing, flags it correctly. Okay, so we'll see plenty of examples of that at some point, but just something to throw in the back of your head that the computer does process Boolean expressions from left to right, and as soon as it can make the determination that there is no other outcome rather than true or false, it stops looking at variables. Okay? Now, let me show you one other thing. Actually, we're going to have something called XOR. Okay, XOR, does anybody know what that stands for? Another Boolean operation, but we've all heard of ands and ors, right? We use those all the time in our normal language, right? Like, hey, I'm going to do this, and then I'm going to do something else. You know, like I'm trying to decide between doing this or doing something else. We use ands and ors all the time, but we don't really use exclusive ors, right? An XOR is an exclusive OR, which means is true only when exactly one side of the expression is true. So this would be false if both sides are true. So true or, here, I'm just gonna say XOR here. It's actually not syntax for C++. C++ has a bitwise XOR, but it doesn't actually have an XOR operator. So this is more for academic knowledge, not really something you'll program with. Okay, so true XOR true is actually false because there is more than one side that's true there. Since both sides are true, it does not fire true for an exclusive OR. True XOR false is true. False XOR true is true. And false XOR false is false. All right. So just kind of store away this whole exclusive OR thing. It's a knowledge thing that does come up in computer science. You'll run into it reasonably often when you get into the computer organization and architecture class next semester, when you start talking about how like different thing components inside the computer actually work. They'll build things using when we're really talking about like hardware devices. If you were creating your own computer hardware devices, there's these little chips, these logic gates is what they're called. We have AND logic gates, we have OR logic gates, we have XOR logic gates, we have not OR logic gates. So some of these guys, we have NAND gates, that's not AND. So if you've ever followed any of the big tech companies when they're from a financial side of things, and you see that they bought a zillion NAND gates from some company in Taiwan or something like that, and you wonder, well, why don't they have AND gates and OR gates and all these things? They pick a generic gate that they can use to build all other gates, and that gets their cost per item down and things like that. Okay, not really something that we need to be concerned with in here. Just know this exists. All right. All right, so then we have our coding caveat that we operate from left to right when we're boiling down Boolean expressions, and as soon as the computer determines that you can only have one outcome, it stops checking. All right, so now let's look at weird stuff. Hide that. Online GDB. All right, let me change this to C++. I'll go and add my using namespace std up there so I can just say cout instead of std : cout. All right, we'll go ahead and run this real quick, make sure hello world's working. It is, so everybody's happy. All right, so now we can go and experiment with some stuff. So let's do a couple of things. We'll define a couple of variables. We'll say bool, let's call this guy is sunny. That's true today, right? Bool is cloudy. That's false. All right, so we'll go ahead and do a cout. And we'll just put a little, we're going to say sunny. And then we'll tack on whatever the current value of sunny is. All right, so when you use cout and you use these little angle brackets, we're gonna output this word followed by a space, followed by whatever this variable resolves to, followed by an end of the line. So this is how we can kind of build out formatted text, or one way we can build out formatted text. So if I run this, we'll see that, is it sunny? It gives me a 1 because true is 1, false is 0. Modern languages, it'll actually say true or false. But ultimately, we've learned in here that everything behind the scenes is stored as a number anyways. All right. And if we steal this line and we just update that to say cloudy, and then we output is cloudy, we'll see that that guy will be false or a 0. So there's that. Let's add a couple more Booleans here. Boolean is warm. It's relatively warm today. Bool is cold. We'll say that's false. All right. So now let's create some outputs. So we're going to say cout. Let's go sunny. And this text isn't required. We're just kind of labeling what we're doing. So we're writing out to the screen the words sunny and warm. And then we'll create our Boolean expression. So that'll be is sunny. And you don't actually need the parentheses here. I'm just going to emphasize that this is going to boil down to a single thing. So is sunny and is warm. All right. So this is the and operator. So is it sunny? Yes, it is. Is it warm? Yes, it is. Is it sunny and warm? True and true is what? True. So it is sunny and warm. So that gives me my true. Make some sense? All right. Now, and this is kind of where it gets extra weird. I'm going to do cout. Actually, let me do the same. I'll have to think through what the output of this is going to be. Let's say I forgot to put the second ampersand. And so this would be a common syntax error, right? Especially as a beginning programmer, you might just put 1 ampersand instead of 2. Well, all of a sudden, that's no longer the same operator. A single ampersand, as we mentioned at the end of last class, is the bitwise operator. All right. Now we see we get the same value here. So we might be, so notice we did not get an error. We see we got the same value, but we got it for the wrong reason. All right. And I'm going to show you what I mean by that using a different example. So cout, we're going to say 7 and 4. Now, right off the bat, we look at that and say that doesn't make sense, right? Because we've mistakenly put a single ampersand. That doesn't even mention that we've put numbers on both sides rather than Booleans. Okay, but in C++, Booleans are stored as a false is 0, and we see a true being 1. But the reality is that by formal definition, true is anything other than 0. So false is 0, true is everything else. All right. So technically, this is a legal Boolean operation. If I say 7 and 4, that might scream at us here since it knows this doesn't make sense. But notice it didn't. It still gave us an answer. So we look at this and we say, well, 7's a number. 4 is a number. We just looked at our, and we're doing ands here. We just looked at our and truth table. None of those things have numbers on either side, right? Well, I just mentioned that a 0 is false and a true is anything other than false or other than 0. So realistically, what this is true and true. And that's why we got an answer of true. Go ahead.
So for true, you could put like true is equal to 99 and they will spit out 99.
You could, because of what's happening under the hood. I would say you would never want to do that. It's kind of a little bit of a dangerous thing here, right? We've stumbled into something like conceptually as human beings, we think of Booleans as true and falses. And I'm telling you that modern languages like Java and C# make them trues and falses. You don't represent them as numbers. But an older language like C and C++, it kind of reveals what's under the hood for us. Somewhat unfortunately, because as beginning programmers, we're prone to screw up. We're prone to add an extra ampersand, have missing curly braces or extra curly braces. We're prone to do things that never actually make sense if you actually slow down and look at it. But this is a lot of data flowing at you at once, and you're inexperienced, so you're going to be very error prone, right? And what's kind of scary about this, and what I'm kind of preparing you for, but at the same time, convincing you of why C++ is a good first language, is it forces you to really think about what your code is doing, but it's sometimes not going to give you errors when really it should. This would give us an error in Java as well as C#, because it's going to say this AND operator is applicable to Boolean values. You've given me 2 integers. That doesn't make sense. Even though in modern languages like Java and C#, Booleans are still actually stored under the hood as zeros and non-zero, 0 and 1, we can say reasonably, okay? They're still actually stored that way, but it's not revealed to us. It's kind of blocked off from us as the programmer. It's saying, look, if you've chosen the Boolean type for doing this, you use trues and falses, we will handle what that actually means behind the scenes. All right. But C++ and C doesn't handle it the way that it should be handled. It's saying, hey, you're the one who picked 7 and 4 for your true values. That's on you. All right. But now we have the double whammy here. So now I do 7 and 4 for some reason. You know, I'm telling you, you could do this if you know that a 7 is a true value and a 4 is a true value because of that rule that 0 is false and anything not 0 is true. Okay. But realistically, looking at that, you would say that doesn't really make sense. The AND operator, that double ampersand, that seems to only apply to trues and falses. And so I would only really give it things that are true and false from a programmer's perspective. How the computer's representing it under the hood, really not my problem. But in this case, having an understanding of that gives us some explanation of why this guy's not screaming at us. Okay, so we would say that if you wrote this on purpose, it would probably be a mistake. Chances are, while you're if you're coding and you're writing something like this, it's probably because you've done this approach. I think I mentioned it probably last class, is when one of the skills you're going to be learning is debugging your code, and you're going to get a lot of errors, right? When you're a beginning programmer. So you're going to write some code, you're going to get an error. And one thing you need to try to convince yourself not to do is when you have an error, don't just immediately go and start changing stuff. Read what the error says first. You know, I would make the overall statement saying never change a line of code unless you have, I guess it's like let's call it at least an educated guess as to why you're changing it. Okay, you want to have a rationale behind it, because the last thing you want when you're working on your homework is to effectively turn in something that works that you have no idea why it works. You just happen to have tried every permutation of things you could have written until you got an output that looked right, regardless of whether it's right for the right reasons or right for the wrong reasons or whatever. Make some sense? Okay. Especially since we're going to find out on the midterm and the final whether you actually learn the stuff. So it doesn't really matter on the homework whether you get the right answer. The homework is about the experience of learning to code. I hope you get a lot of wrong answers, so by the time you get to the midterm and the final, you've run into a lot of the wrong ways of doing things and kind of beaten yourself up enough that you've kind of started to assimilate the right way of doing some things. All right. So we would say this guy never makes sense. And just here to show you real quick. We take that out. It says invalid operands, int. This operator right here. So because we're trying to write a Boolean expression in here and we're reliant on this guy to finish before we start printing stuff out, we put parentheses around that and we're saying we ultimately want you to print this out, the result of that. So just like normal math, if there's something you want to make sure happens first, throw in parentheses around it and it'll process it that way. All right, so now let's insert a error that we might be prone to. Still forcing this idea of using numbers like 7 and 4 kind of erroneously. I mean, if there's one thing I want you to walk away from this as is 7 and 4 are non-legal Boolean values, even though C++ lets you get away with it. Because under the hood, it stores falses as 0 and trues as non-zero, even though we pretty much think of true as 1. All right. But when I run this, we get the answer 4. Well, before when I had 2 ampersands, using my normal AND operator, I got an answer of 1 for, let's call it the wrong reason, right? So there's my 1 right down here. But now when I did something that we might be prone to do, forgetting the second ampersand, and I do 7 bitwise and 4, we get the number 4. Why? Anybody have a idea of why we're getting this weird number? We just saw it happen twice in a row, so certainly it doesn't seem like this is a magical way of doing a random number generator. I mentioned the word bitwise. What does bitwise mean to you? What is a bit? Bits are zeros and ones, right? A single bit is a single 0 or a single one, okay? Bitwise would mean we're doing something in terms of the bits. So let's look at this as an example and see, why do we get a 4? So if I say 7 and 4, this is 7 bitwise and 4. That's what that actually means up there. Okay. Now, what I'm going to tell you is you will very, very, very rarely ever do any bitwise operations. Okay. You will see them in the computer organization and architecture class you'll take next semester. But professionally, unless you're in a very special kind of industry, maybe writing low-level code for like dishwashers or something like that, where you're actually working with, often they're called embedded systems, which are actually cool because it's like, that's how most of the stuff around us works with embedded systems. But programming for them is actually pretty simple. Because there's far less, they have less capabilities, but you might do some bitwise stuff with that. It's more of a mathy thing than anything else. So what I want to do here is I want to rewrite 7 and 4 in terms of the equivalent bits. All right. So a 7 is a 1, 1, 1. And a 4 is a 1, 0, 0. Correct? This is the 1's place, the 2's place, the 4's place. This is 4 times 1 plus 0 times 2 plus 0 times 1. That's a 4. This is a 7. 1 in the 1's place, 1 in the 2's place, 1 in the 4's place. 4 plus 2 plus 1 is 7. All right, so everybody's good with this is the binary representation of the decimal value 7. And we could get that value by doing our little divide thing, right? You know, if you didn't like just walking through it like that, we can do 7 divided by 2. How many times does 2 go into 7? 3 times. 3 times 2 is 6 with a remainder of 1. 3 divided by 2. How many times does 2 go into 3? 1 time. 1 times 2 is 2 with a remainder of 1. 1 divided by 2 is 0. we know we're done. When you get a 0 right here, 0 times 2 is 0 with a remainder of 1. We read our answer from bottom up, so it's 1, 1, 1. All right, everybody cool with that? So same pattern we've used before. All right, so this is the binary version of 7. This is the binary version of 4. This is the bitwise AND operator, which means what we do is we are performing the AND operation on a per bit basis here. That is 1 and 1 is 1. True and true is true. True and false is false. True and false is false. 1, 0, 0 is the number 4. Make sense? That's where that 4 came from. Go ahead.
Wait, so we add together 1, 1, 1 and 1, 0, 0, but the 1, 0, 0 overrides the 1, 1, 1. How?
We're not adding them. We're not adding them together. We're saying this one and this one. So a 1 is a true, a 0 is a false. So if I say true and true, I get a true. If I say true and false, I get a false, because trues are only true when both sides are true. If I say true and false, I also get a false. So this final value of doing a bitwise AND between that number and this number, where we're doing an AND on a per bit basis, we get a 1, 0, 0, which if we convert that back to decimal is a 4. That's why our output was a 4 in this case. It had really nothing to do with working with Boolean values. It had us performing the Boolean AND operation on a per bit basis of those numbers.
Okay.
Okay? And again, I'm telling you, this is something that really does not apply to this class in terms of logic you'll ever do. In fact, you might go your entire career and never, ever, 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 ever do this. So why am I showing it to you? For the reason that you may run into a beginning programmer mistake when you use a single ampersand rather than a double ampersand, and you get an output rather than a red error, and you're like, what the heck is going on? We just explained what the heck is going on. Make some sense? All right. I'm not going to test you on that. I want you to stick it behind you, stick it in your storage bank somewhere. Kind of remember that there's this bitwise operation thingy. All right. And that bitwise operation thingy does mathy stuff with numbers instead of binary stuff, but it does it by way of binary stuff. Because we can also get that guy. So another reason I put this, if you had never learned this, if I hadn't taught it in class and I said, oh, well, you're going to do some number. So in this case, you read this and most of us would look at that and say, oh, that's how you might say 7 to the 4th power, right? Reasonable enough sense. We've seen that be correct enough times. That's not how programming works. That is not 7 to the 4th power. 7 to the 4th power is 2,401. We'll go ahead and run this. And of course, we get 3. Close enough. Maybe a rounding error. Big rounding error, right? All right. So why did we get a 3? Exact same reason. So let's take this slide. We'll duplicate it. And we'll do bitwise XOR. That's what that caret is. It's the XOR operator on a bitwise level. We don't actually have an XOR operator. We have a way of accomplishing it. Some newer languages do have an XOR operator, but it's one of those things that you actually are not going to run into all that often. Your bread and butter when you're dealing with Boolean stuff for normal programming things is ands and ors. So our whole world as C, C++, Java, C# developers really revolves around that double ampersand and the double vertical bar for ands and ors. All the stuff we're talking about right here is when we screw up and start wandering outside the lines a little bit, even though there are reasons for this, they're not reasons we're likely to run into potentially for our entire careers. But there are computer organization and architecture reasons where this could make sense if that ends up being the world that you land in. But let's see what this means. So this is a bitwise XOR. So we still have 7 represented as 111. We still have 4 represented as 100. So 1 XOR 1. Remember, an exclusive OR says that exactly one side is true, not both. So true XOR true is actually false, because both sides are true. That breaks the rules of XOR. True XOR false is true. True XOR false is also true. 0, 1, 1. This is the ones place. This is the twos place. This is the fours place. So 0 times 4 plus 1 times 2 plus 1 times 1 is the number 3, which is what we got right here. Make some sense?
Go back to that.
Nope. Good. What's up? And these slides update in real time on the as long as I keep hitting save. So if you follow the link on Blackboard for the slides, you'll see them updating. Not that you can't take notes, but you'll always have the stuff. All right. So questions about that stuff? All right, so we can kind of throw that to the side and say, hey, when I screw up, but it doesn't actually yell at me, but I get weird results, there's probably an explainable reason for it. All right. But as a beginning programmer, we're going to kind of be prepared that we're going to screw up like this. And one of the reasons I pick a language like C++ is it's much, much pickier in a lot of situations. So it'll give you errors in time in situations where maybe a newer language might kind of protect you. But at the same time, it also does things that when you meant to say one thing, but you actually said something else. That's a common trait of a beginning programmer, right? In your mind, it made sense what you wanted to do, but you had trouble translating it from what's in your head to the equivalent code. That's going to be something many of you are going to struggle with for a while. Okay, and your evidence of that is when you do your homework and you're ticked off at Littman that he's making you spend so much time on your assignments, okay, and you're not any good at this, you're never going to become a programmer, yada, yada, yada. Then you come to class and you see me solve it in 5 minutes, like, that was it? Are you serious? As long as it's making sense when we solve it in class, you're just fine. It'll eventually get to the point where you're able to do it on your own. That's the last part that happens. Make some sense? Just like watching sports. When you're really into a sport, you can gain an appreciation for what these professional athletes are doing in that sport, and you understand the strategy when you see it, but you might have trouble executing that if you were the one out there playing the sport. Make some sense? All right. But you're not really putting the reps in to be a football player or something like that necessarily. So, but we're putting the reps in here. So our goal is to eventually get to the point where we're able to do the strategies ourselves. All right. So we've seen these operators, or Boolean operators, the AND operator, the OR operator, and the NOT operator. These guys are the ones that we're going to see the most often. Okay. These are our, in fact, I'm going to expand this a little bit. I'm going to say these are our logical Boolean operators. Because we also have other Boolean operators that you've seen before in your math classes. Let's get rid of that guy for now. So let's do arithmetic Boolean operators. So these are guys like less than or equal to, greater than or equal to, not equal to, and equal to. All right. So those first four, we all have seen those in math classes for a long time, right? Is 5 less than 7? Yep, that's a true statement that 5 is less than 7. Okay. Is 5 less than 5? Nope. Is 5 less than or equal to 5? Yep. Okay. Works just the same way as you do in your normal math classes. Not equal. Here. Not equal is true when the values on either side are not the same. This is the equivalence operator. So this is another point of weakness for beginning programmers. We're used to an equal sign meaning an equal sign, right? Can you imagine a world where if what's actually required to compare two numbers or two values together requires two equal signs next to each other, might we be error prone and maybe only putting a single equal sign? So if we're looking at the code version of this, if I say cout 7 equal 8. Is that a reasonable thing where we might screw up and put a single equal sign rather than a double? So if we look at this way, is 7 and 8 the same value? They're not, different values. So we expect this to give us a 0, right? A false. We'll run this. There's our 0. 7 and 8 are not the same value. What about 7 single equal sign 8? A single equal sign is the assignment operator. So it says take whatever value's on the right and assign it to the thing on the left. Now the issue is the thing on the left in that case has to be a variable. 7 is not a variable, right? 7 is a hard-coded number that is built into the language because 7's already a thing. And in real life, could we just redefine the value of 7 to be 8? We don't get to make up the rules of math, right? They're already set in stone. So if we look at this and we say, okay, well, 7 gets the value. Sometimes I'll read this as gets the value, that assignment operator. 7 gets the value 8. That doesn't make sense. And when we run this, we see that C++ agrees this does not make sense. It says the left value required as left operand of the assignment. So it's saying this left value 7 has to be a variable. It has to be something that we can assign a value to, where we can think of the number 7 as kind of being read-only. We can't update the value of 7 because it already has a hard-coded value that just God made. All right. But 7 equal 8. This is our equivalence Boolean arithmetic operator. This is saying, is 7 and 8 the same value? It's not. We expect a false. In C++, a false is represented as a 0. There's our 0. If we wrote that identical line of code in C# or Java, instead of a 0 here, it would just say false. It would do the translation for us. All right, questions about that? Similarly, if I say not equal to is is it true that 7 and 8 are different values? Absolutely. So we expect to get a true value here. which our experience thus far has been, as long as we are out of the equation, a true is represented as a 1, right? Even though I've told you that the official under the hood rule for Boolean being represented as numbers is that 0 is false, anything other than 0 is true. But we expect a 1 here, that 7 and 8 are different values. So it is true that they are not equal to each other. Therefore, we got a 1. All right, everybody good with that? What about 7, not 8? Wasn't happy with that. So we don't have a bitwise not operator where we go through and because not is not something that not is not something that can be done between 2 bits. Not is a single bit flip. Not 0 is 1. Not 1 is 0. Okay. So with that in mind, we know that 7 is not equal to 8. We expect a true out of that, like we got there. But what if I took that true and I knotted that? Not true is actually false. All right, so I took whatever the output was of this, which we said, hey, a 7 and an 8, different values, so 7 not equal to 8, that is true. We got a 1 out of that. And then I have a not in front of that whole thing, so not true is actually false, which is what we got right here. Make sense how this is working? All right. So punchline there is pay close attention with the equal sign as to whether or not you are trying to assign a value to a variable or you're trying to test equivalence between 2 values. Equivalence requires 2 equal signs. Assigning a value requires 1 equal sign, but the thing on the left has to be assignable. Means pick a variable. Okay, not a hard-coded value that really can't change. Okay, so we all have a strong understanding now of, at least academically, of working with Boolean values, Boolean operators, creating Boolean expressions. Okay, and we can make these guys look scary. We can come in here and we can say, well, not 7 not equal 8 and is sunny, or actually let's do it this way, and is warm. Is that a Boolean expression? What's a Boolean expression? Any expression that boils down to a single value of true or false. Is that a Boolean expression? It's a lot of crap there. When you first glance at it, it's like, okay, well, I mean, that's not a single value, right? But if we step through it, let's copy it here. We step through that guy. Let's look at this first part. Is 7 not equal to 8? That's a true statement. So this is not true. And is sunny? Our value of is sunny is true. True. And is warm? Is warm, our current value of is warm is true. Looks like that. Not true is actually what? False. And true and true. False and true is false. In order for ands to be true, the whole thing has to be true. And as soon as we hit a false and we have the value and after that, it knows to stop. So this whole thing will be false and true, which is false. Is that a single value of true or false? After we brought it all the way down, it's one value, true or false. So that's a false. When we go to print this out, we expect to get a 0. And there's our 0. What's the lesson there? Is don't immediately think you know what something says until you've actually resolved it yourself. Sometimes scary things boil down to simple values. Okay? And through experience, you'll get better at that, where you will be able to just glance at it and say, okay, well, there is more than meets the eye there. Okay, but for a while, we want to, because we're trying to drill ourselves into thinking more like a computer. If you go back to the first week of class, we talked about why is programming difficult? Because human beings are really good problem solvers, but we have trouble articulating how we solve problems. Okay, because we spent our entire life interacting with human beings and solving problems with human beings. We're not used to thinking like a computer has to logic through things. So in here, you're going to get better and better and better at thinking like a computer. Hopefully you can still hold on to your humanity and still deal with normal people. But that's kind of one of the I don't know, the funny things with software engineers. Like they don't want them dealing with normal people. Let's keep them in their sweatpants in the back, with hot pockets and soda. We'll have somebody else interacting with people. But every now and then you actually get functional human beings that are also software engineers, but you get the point. The more you start connecting with the computer and seeing things through the same lens as the computer, kind of the more logical you might end up being with human beings, and they might stop liking you, is what it comes down to. All right. So we're good at Boolean expressions now. So now what do we use Boolean expressions for? We're going to use these guys for conditionals. So that's asking questions. And loops. That's repetition. So this idea of a Boolean expression is the core component of the rest of our how do human beings solve problems. So let's look at conditionals. We'll say asking questions. This is a conditional, usually an if else statement, kind of what we would typically call it. All right. The syntax for an if statement is the word if, all lowercase, opening parenthesis, Boolean expression, close parenthesis, then opening curly brace. We're going to talk about the curly braces here in a minute. Then logic when Boolean expression is true. Eventually closing curly brace. And then optionally, else, opening curly brace, logic when Boolean expression is false, closing curly brace. And this else is a lowercase e. All right. And else is not always required. Sometimes you can just say, I'm going to ask a question and I'm only going to do something if the answer to that question is true. Make some sense? All right. So this else is an optional thing. So now we already know what Boolean expressions are. So we know what's going to go in this little thing right there. Could be something simple, could be something complex, but ultimately it'll boil down to a single value of true or false. And if that's true, we will do all the stuff in between this opening and closing curly brace. All right. So now let me rewrite this slide slightly. Rewrite here. So technically, the curly braces are actually not a formal part of the syntax. An if statement says, if some Boolean expression is true, perform this statement, which is what you want to do when it's true. Otherwise, else, perform this statement, which is what you will do if it's false. Now, in situations where you're only going to do a single thing that you can express in a single statement, the curly braces are actually not required. But would you agree that more often than not, if you're asking a question, you're probably going to do several things in response, or at least something more than one? It's going to be a common occurrence, right? Well, that means that I have to have some way of representing a single statement with more than one thing in it. So here we'll ask the question, is it common to do more than one thing as a result of a Boolean expression? Yes. So then we might say, how do we create a single statement that that gives more than one instruction to the computer? We do this with something called a block statement. And a block statement is opening curly brace, statement 1, statement 2, say dot, 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 statement X, closing curly brace. So if we want to say more than one thing, we can use a block statement where we have a list of statements inside of there. Each of them is ending in a semicolon, surrounded by curly braces. Make some sense? So it would be very, very, very common for us to look at if statements and see curly braces. But if they're only doing one thing, technically, a curly brace is not needed. But let me ask you this. If I have a block statement like this, but I only actually put one thing in it, is this still a collection of statements? Technically, a block statement is a collection of 0 or more statements. Is that a block statement? Yep. Is that a block statement? Opening curly brace, closing curly brace. Not an overly interesting one. Not one that's going to produce usable results. Still a block statement. Okay. So my argument would be, and let me show you kind of the rationale here before I make this argument. So if I go back in here, and let me, here, let's just get rid of this and let's put some if statements in here. If I say if is sunny and is warm, opening curly brace, see out, it is sunny, see out, it is warm. See you out. Let's go outside. When I run this code, remember all programs begin and end with main, right? So we start right here at line 15, very first line of main. What are we doing is if I run my program with just that stuff in it, if that's my entire program, what's my output going to be? If I hit run, is it going to have any output? Nope. That doesn't mean this thing didn't work. It just means none of the things I said here resulted in something showing up on the screen. I created 4 locations in memory and put some values there, and then chose never to use them. What about now? What's the output of this going to be? Is sunny true? Is warm true? True and true is true. So since this whole thing boils down to true, we will execute this block statement. So we're going to see it say it is sunny, it is warm, let's go outside. Oh, here. Expected semicolon before this guy. I had actually forgotten. Well, I didn't forget it. I typed the wrong thing. So I had a syntax error there with an exclamation point. I needed to end that line with a semicolon. So those are examples of errors you'll get. So it is sunny, it is warm, let's go outside. That's what printed out here. Okay. Now what happens if I change is sunny to false? I didn't change this code at all, but I did change one of the values up here. So now false and true is false. So my output now will be nothing, right? Okay, we still ask this question, but because this boiled down to false, we did not do that code there. Now I could throw an else. See out. Let's play video games. And now we'll get that output. Let's play video games. All right. So let's look at something here. Let's say that we didn't put those curly braces there. We're not respecting the curly braces. All right. Now, how many of you have our Python, or I say our Python program, how many of you have coded in Python before? Okay. Remember, I assume you've never coded before, so don't worry if you couldn't put your hand up. Python, the only thing, in my opinion, it has going for it for beginning programmers is that it forces indentation. When you look at this code, don't these 3 lines, because of their indentation, look like they belong to this if statement? Visually, they look like they belong there. Python doesn't require curly braces because indentation tells the story for them. So in Python, if I were to write an if statement, it'd be the exact same thing as this, except I put a colon there and I spell out the word and here. Otherwise, this is Python code. All right. Remember, all programming languages are the same. All right. So just because these guys look the same, look like they all belong to the if statement, because the syntax for an if statement is if some Boolean expression followed by statement. There's actually 3 statements here. The only one that actually is owned by the if statement is that very first one. So right now it's printing out let's play video games because I have is sunny as false. But if I run this right now, is it going to be an error? What's it going to print out? Well, and Is it going to print out it is warm? Is it going to print out let's go outside? So notice we get an error here, but why? Because this else is now disconnected from this guy because of all of these statements. So just to show you what I'm talking about here, let me just get rid of that for a second. So now, is sunny is false, is warm is true. This if statement is false now, correct? At a glance, we might say, oh, the output's going to be nothing. But the output will actually be, it is warm, let's go outside. It is warm, let's go outside. Why? Because only this very first line was actually part of this if statement. Because the syntax for an if statement is if Boolean expression statement. Now, if I go in here and I just say, okay, well, I really meant for those things to all go together, which in languages outside of Python, indentation doesn't matter. I can have all this stuff on a single line if I want. So if I go ahead and wrap that in curly braces, making it a block statement, now this is the statement that goes with this if statement. And notice a lot of these IDEs, they can have a thing where you can kind of like minimize it. All right, so this is the statement. So all I changed here is put the curly braces in, but now when I run it, you're going to see these two lines disappear. Because now this entire statement is part of this if statement, not just the first line. So the reality of this is that the way this was actually treated is as if I wrote it like that in Python. So Python forces us to indent to make things belong to other things. The only thing that actually belonged to this if statement was that first cout. These other guys just happen to be in close proximity, but we're actually not governed by the output of that if statement.
Wait, so shouldn't they all have been printed to the screen instead of disappearing?
No, because this first line, here, let me just put it back.
Oh, because one is false, both aren't true.
When I have it written this way, because this thing is false, none of this happens.
Okay.
So that's why nothing prints to the screen right now. But when I remove the curly braces, like that, now this is false. So we might assume that this stuff doesn't happen then, because visually a human being might look at this and say, okay, well, all of this stuff is what we want to have happen when this is true. And if this is false, we want none of this stuff to happen. But if I run it right now, these two things still happen, because the two things I have highlighted right now are actually not connected to this if statement. They just happen to be in close proximity, but they're not part of the logic of that. So when I run this, yes, this is false. So we did not execute that line. But these two lines still executed because they weren't part of any if statement. So my question would be, is it ever wrong to use the curly braces? Typically, when we're writing if statements, if statements, we are going to put the lines of code that we want to be associated with a true statement together. We should indent them so it looks good, easy for human beings to read at a glance. When we look at this, regardless of the curly braces, at a glance, we see these guys indented underneath this if statement. So they seem like they go together, right? But they only actually go together if I have them inside of a block statement. If I only put one line of code inside of a block statement, that's still allowed. No problem. Even though the curly braces weren't absolutely required in that situation, It's perfectly fine for them to be there. And I'd make the argument that having the opening and closing curly brace here kind of shows you where the if statement begins and where the if statement ends. Now, sometimes what you'll see is code that looks like that, where they actually put the starting curly brace on the same line as the if statement, which is fine. You'll see plenty of examples that look like this. In fact, I would even say that many modern programmers have adopted this format. I think this format is bad. I mentioned a little bit ago that C and C++, all our modern languages, they don't care if you write your whole program on one line. They're fine with that. So this is really for human eyes only. I think this does not look as good as that. Because when we put it this way, we can see here's where the if statement begins, here's where it ends, everything in between is kind of like the meat of the sandwich. All right. When we put this guy up here, you still mostly get that feel. Okay. But this syntax actually exists from a long time ago when we didn't have the internet and all this stuff was in books. We just saved one line of printing. So in books, they would skip that, they would retrieve that one line by putting the curly brace up on the same line. And now it's become kind of normalized. I don't actually care which way you do it. You're not going to lose points. But I do want you to indent your code and format it reasonably. But I would encourage you to put the opening curly brace under this guy. Because one thing that you will end up doing, you'll see me do it, is whenever I write an if statement, I always immediately put the opening and closing curly brace. And notice here that the IDE actually does that for you. So basically, I say an if statement, I get my 2 pieces of bread out, and then I start putting the stuff in between. Then you won't forget closing curly braces, which is going to be a common beginning programming mistake. All right, so homework over the weekend. I'll be putting it up here in a little bit. It's gonna be similar to the first assignment, except you're gonna be defining some Boolean variables, writing some Boolean expressions, writing some if statements that do stuff, giving yourself the opportunity to make syntax errors and things like that. We'll come back next week. We'll go through that. We'll get into loops, and then we'll start solving some legitimate problems. All right? Questions, comments, concerns, bribes? All right, look for that assignment sometime up in the next couple hours. I have a meeting right after this, and then I'll get it up.
Have a great day.
Yep, you have a good one.
I do have a question about